Hello everyone, my name is Mo Xu. Today I'm honored to present our work of zero streaming cameras, a new paradigm for video analytics systems. Let me first introduce some well-known trends of surveillance cameras. Local and wireless cameras have been growing exponentially, and their large-scale deployment along with the machine learning technique has enabled ubiquitous intelligence. For example, a user can query all the frames that contain the object of interest, like a bus. But given such large volume of videos being captured every day, how much of them have been used? So unfortunately, we find most videos remain cold, which means those videos are never used until they expire and get deleted. So here we analyze the video usage of a campus in China and find only less than 2% camera streams and even less video data have been queried. So this is because interest events are often unforeseeable, like car accidents, and the need for examining such events emerging well after the fact. Of course, transmitting those cold videos to a central server wastes a lot of precious wireless bandwidth, noting that the video data is large, 24/7 always on, and we are talking about very large scale and dense deployment. So even if edge servers are used, you cannot avoid the waste of wireless spectrum, which are very limited and should only be provisioned to those user-centric applications, like playing video games instead of transmitting cold camera videos. Fortunately, we find the storage is getting larger and cheaper. With a few tens of dollars, you can buy an SD card large enough to store weeks or even months of video data. So that's enough, and also the status quo for most video scenarios, because the regulations in many states do not allow the video backup for too long. With those trends, we propose an extreme design called zero streaming cameras. We want the cameras to store all videos on local storage during video capture, but only respond to servers during query time. So this new paradigm allows the network and the computer resources being provisioned on demand, making it extremely resource efficient, given that most videos will never be queried. The key question this work is about to answer is that how fast can we query the zero streaming cameras? The multiple challenges we are facing here, for example, the cameras are low cost, wimpy, their hardware is like a Raspberry Pi. The network bandwidth during query time is limited, and there will be the bottleneck of the end-to-end query speed. So finally, once a query has been issued, the users will be waiting, and we want to deliver useful results as fast as possible to the users. We have built a runtime system spanning camera and the cloud for fast video query on zero streaming cameras. The system has two key techniques. First, during capture time, it builds landmark frames to capture reliable video knowledge to accelerate future video queries. And second, during query time, it runs neural networks on cameras to prioritize or filter the frames to be sent to the clouds. And it also keeps updating the neural networks running on the cameras. So more details will be explained. DIVA now supports three kinds of basic query types called retrieval, tagging, and counting. A concrete query specifies the time span that the users want to query and the object of interest. For example, a retrieval query will return all the frames that contain this object to the users, and the tagging query will only return the time ranges when such object appears in the video to the users. The more advanced and complicated queries can be built atop those three basic query types. In the rest of the talk, I will mostly focus on retrieval query as an example. I want to emphasize that the key designs of our system are valid to different video query types, although there are few ad hoc policies to be tailored for those query types. So another key concept we introduced into DIVA is what we call query online refinement, a concept borrowed from the database community. It means the system should deliver incomplete but useful results to users as early as possible so that the users can inspect them at first hand. Then the results can be continuously refined until the users are satisfied. So the techniques we built for DIVA will center around this key idea. So DIVA uses the concept of operators, which are just small neural networks that can run fast on cameras, fast enough to match the speed of frame uploading. The key opportunity exploited by DIVA is that those operators provide very rich trade-off between the model speed and the model accuracy. So how operators are used in DIVA? To fully utilize the network bandwidth, DIVA will keep streaming video frames from the cameras to the cloud with the uploading queue. So the order of frames being uploaded is very important. Taking retrieval query as an example, operators are used as rankers that will give a score between 0 to 1 to each video frame. The score is used to prioritize the frames in the uploading queue. So in this way, the frames that are more likely to contain the object of interest will be uploaded earlier. The first key technique of DIVA is landmark. So basically, the camera will run the expensive object detector on the capture frames regularly. So because of the limited computing power on cameras, the landmarks are sparse. For example, one in every 30 seconds using ULO v3 on Raspberry Pi. So those landmarks are already tagged by the expensive model, so they can be used to bootstrap the operators as training examples during the early stage of the query. The rest of the frames will be further processed as the query goes on. But more importantly, the landmarks provide us useful video knowledge, or the spatial object skewness in this case. We find objects of a given class are likely to concentrate on certain small regions of video frames. For example, most cars appear near a stop sign, and most persons appear in a shop's aisle. By cropping the input frames with those important regions, the operators can focus on those regions with more important and compact information, and so it can achieve much better accuracy at the same speed as this right figure shows. The second key technique of DIVA is operator upgrade at query time. As we mentioned, there are so many operators with a rich accuracy speed trade-off. So which one should we choose to achieve the optimal performance? We find there's no silver bullet. At early stage, the fast but inaccurate operators perform better because they can quickly explore all the frames and identify those positive frames that are easier to be detected. It means more positive frames can be uploaded to the users at early stage. However, as the query goes on, the remaining positive frames are more difficult to be detected. So we need more accurate operators to refine the ranking results on the cameras. To ensure the best performance throughout the whole query process, DIVA uses multiple operators from cheap ones to the expensive ones. During the query, the camera keeps running operators and uploading the ranked frames. The server receives the frames, using them to train more accurate and expensive operators, and downloads the new operators to the cameras for uploading. So all those processes run in parallel. So here we explain the concrete query process. Once a user issues a video query, it will be delivered to the cloud and also the cameras that are queried. The cameras send landmarks to the cloud to bootstrap the first operator, which will be downloaded to the camera for local processing. The camera then uses this operator to rank the frames and also sends the ranked frames to the cloud at the same time. The frames being received on cloud will also be processed by an expensive Oracle model as safeguard. So only those true positive frames will be returned to the users. So using the frames and the process results as the annotations, new operators will be trained on the fly and then downloaded to cameras for upgrading. During the whole process, the query results will be continuously refined to the user, and the user can abort the query anytime she finds the results satisfactory. You may notice some important questions have not been answered, such as when should we upgrade an operator and which operator should we upgrade to? So due to time limit, you may refer to our paper for more details. There are two more things I want to highlight. First, I've only discussed how DIVA handles query on one camera. So to query many cameras, we can just provision more GPUs to DIVA to make sure that the server-side computation will not become the bottleneck of the end-to-end query speed. And second, DIVA is in an extreme design space in video analytics systems and is complementary to the systems in other design spaces. So in real world, these could coexist to handle different video scenarios. For example, real-time video analytics systems should be deployed in a small number of critical regions like banks, but DIVA can be more densely deployed on streets for its resource efficiency. So next, I will highlight some of our experiment results that demonstrate the efficiency of DIVA. So we downloaded 15 public video streams, each of which spans 48 hours. So we use two typical camera hardware and powerful server GPUs to build the system. We also built several competitive baselines by borrowing the key ideas of previous state-of-the-art video analytics systems. So overall, we find DIVA can run at hundreds of real-time and outperforms baseline throughout the whole query process. So in this figure, we show how fast the system can retrieve images containing bicycle. The red triangles indicate when DIVA upgrades to a new operator. On all tested videos, DIVA can reduce the end-to-end query latency by 4 times to 30 times over the competitive baselines. Only in very few cases, DIVA underperforms at early stage of the query because it needs to bootstrap the operator. And so the cold start can take a few or tens of seconds. We also separately evaluate the improvements brought by DIVA's two key techniques. It shows that for different query types, both landmarks and operator upgrade can reduce the query latency by a few times. We also compare DIVA to all streaming, which means the traditional approach that uploads all video to server at the capture time. We find DIVA can reduce the network usage by more than 1,000 times in the use case of the campus video system, as previously mentioned. The network saving come from two sides. The first one is cold video that never being queried, and the second one is those being filtered by the operators of DIVA during the query time. Finally, we repeat our experiments with different camera hardware. The results show that DIVA can tolerate sparser landmarks with acceptable performance degrees. However, using cheaper neural networks to build inaccurate landmarks causes significant performance drop. So with limited on-camera computational capacity, it motivates us to build reliable, accurate, but sparse landmarks. So to summarize, we propose a new video analytics paradigm of zero streaming for high resource efficiency, especially the network bandwidth. We have also built a runtime system for such a new paradigm to achieve a high query speed. So beyond video analytics and the camera, we believe such zero streaming paradigm will be more and more pervasive in the future because the data is growing faster and faster, but the network cannot keep the same path and Moore's law has been dead. So we believe data decentralization on edge devices is the future, and how to query those data efficiently will be an important and emerging research direction. Okay, that concludes my talk. I want to thank my collaborator, Tiandu, Yunxin, and Felix, and also thank you for listening.